Hello, everyone, and welcome back to the Deep Dive. If you're listening to this, chances are you have your chemistry textbook open, or maybe you're walking to your tuition class thinking about the upcoming exams.
Yes, and today we're tackling a topic from Unit 9, amines.
That's right. And I know amines can sometimes feel like a small chapter, but it has some really, heavy concepts.
It really does. Today we're focusing on one specific tool that is basically the superhero of organic synthesis.
We're talking about the importance of diazonium salts in the synthesis of aromatic compounds. I know, it's a big title. But honestly, when I first saw this, I just thought, why do we even need this? It seems like such an extra step.
That's the most common reaction from students, why make this salt if I just want to add a chlorine or a bromine? But by the end of this deep dive, you'll see that without diazonium salts, half the reactions in your organic chemistry paper would be, well, impossible.
It's possible. That's a very big claim.
It is.
Okay, so let's start where we always do. Let's set the scene with a scenario. I want you to just imagine a chemistry practical exam. You've got two students, let's call them student A and student B.
Okay.
They have the same aim written on the board. Prepare chlorobenzene starting from aniline.
Ah, a classic conversion problem. Aniline to a halorine.
Exactly. So student A, he looks at the aniline molecule, he sees the benzene ring, he sees the amino group, and he thinks, simple logic, I'll just take chlorine and mix it directly with the aniline.
The direct approach, direct halogenation.
Right. He thinks aniline's reactive, chlorine is reactive, let's just put them together. And what happens?
He's a disaster, an absolute disaster.
He gets this black, sticky mess in his test tube. He doesn't get chlorobenzene at all. He gets a mixture of products chlorine attached at the ortho position, the para position, maybe both. It's what we call a polysubstituted mess.
And he fails the practical.
He fails the practical, and he probably gets a scolding from the external examiner also. Now, look at student B. She takes a totally different route. She doesn't touch the chlorine yet. First, she takes the aniline, she cools it down in an ice bath, adds some specific reagents, and she converts it into this diazonium salt. Then she adds the reagent.
And the result?
Perfect. Pure chlorobenzene.
So student B clearly revised her name reactions properly.
Clearly. So the mission for today is to understand why student B won. Why is this diazonium salt the magic switch that fixes this problem? Why did student A fail so badly?
That's the perfect question. And the answer, really, it lies in understanding the nature of aniline itself. And this brings us to our core idea.
Okay, let's break it down to the zero level. Why did student A's direct method fail?
So think about the aniline molecule. You have a benzene ring, and sitting on top of it is the NH2 group, the amino group, right?
Right.
Now, in class 11, you would have learned about resonance and the plus R effect.
Yes, the resonance effect. The nitrogen pushes its electrons into the ring.
Exactly. That nitrogen has a lone pair of electrons, and it's very, very generous. It just pushes those electrons into the benzene ring. And this makes the ring incredibly electron rich. It activates the ring.
Activates it, so it becomes something like a super magnet.
That is the perfect analogy. Aniline acts like a super strong magnet for any incoming electrophile, basically anything that wants electrons. So when student A throws chlorine at it, the ring is just too excited. It doesn't just take one chlorine atom. No. It grabs chlorine at the ortho position, at the para position, sometimes at all of them at once.
So it's a case of over-attraction. Like, you invited one guest, but the entire colony showed up at your house.
Precisely. You get 2,476 trichloroaniline, which is a white precipitate, but it's not what you wanted. You wanted chlorobenzene specifically.
Yeah.
You can't control the reaction because that magnet is just too strong.
Okay, so we need a way to turn off the magnet, or at least, control it.
And that is exactly where the diazonium salt comes in. The process of diazotization, it changes the entire personality of the molecule.
How does it change it?
Well, when you convert that amino group, the NH2, into a diazonium group, which is N2 plus Cl, you're replacing a group that gives electrons with a group that is just desperate to leave.
Desperate to leave? What do you mean?
This is the chemical secret. The diazonium group basically has nitrogen gas, N2, trapped in a bond. Now, nitrogen gas is extremely stable, right? It makes up 78% of our atmosphere.
Right, it's very inert.
So chemically speaking, that N2 group on the ring is thinking, I don't want to be attached here. I want to be free. I want to fly away as a gas. It is the world's best leaving group.
I see. So the ring is sort of holding onto this nitrogen, but the nitrogen is just struggling to break free.
Exactly. So if you offer the ring a new partner, like a chlorine atom or a bromine atom or a cyanide group, the ring says, okay, fine, come on in. And the nitrogen says, great, I'm out of here. And it just bubbles away.
Wow, that's a brilliant way to visualize it. So it's a swap, the nitrogen leaves, and the new group takes its exact spot.
And because it's a specific swap, you get selective monosubstitution. You don't get a mess. You get exactly one group replacing the nitrogen.
So for the students listening who need to write a proper definition in their board exams, what is the anchor definition?
Okay, you should write this. Diazonium salts are invaluable in aromatic synthesis because they bypass the problem of overactivation in amines. They enable selective monosubstitution of aromatic rings and facilitate functional group interconversions that are impossible by direct methods.
Selective monosubstitution. I
Yeah.
think that's the key phrase that will get you the marks. Now,
Absolutely. That's the main thing.
before we talk about the reactions, we have to talk about making the salt. You mentioned student B used an ice bath. This is a very crucial detail, isn't it?
It is the single most important condition. If you are writing the preparation of benzene diazonium chloride and you do not write the temperature, you will probably get 0 marks for that step.
0 marks just for missing the temperature.
Yes. The reaction between aniline, sodium nitrite, and hydrochloric acid must happen between 273 and 278 Kelvin.
Which is 0 degrees Celsius to 5 degrees Celsius.
Correct. Ice cold. It has to be.
But why is it so fussy? What happens if I do it at room temperature, say 25 degrees?
Well, remember how we said the nitrogen is just desperate to leave?
Yeah.
If it gets even a little bit warm, that nitrogen gets enough energy to just break the bond immediately.
Yeah.
The salt decomposes before you can even use it. It will react with the water in the solution and turn into phenol, and you just lose your nitrogen gas.
So this superhero tool just falls apart if it gets warm.
Exactly. It is thermally unstable. You have to keep it on ice until the very moment you're ready to use it.
Okay, that is a big clarity check for everyone listening. 0 to 5 degrees Celsius. Don't forget it.
Now that we have our unstable, ice-cold diazonium salt, let's talk about all the amazing things we can do with it.
Yes. In the notes, we have this amazing visualization called the synthesis wheel.
Yes. This is the best way to memorize the reactions for this unit. I want you to close your eyes, unless you're driving, of course. Picture a bicycle wheel.
Okay, got the wheel in my head.
At the very center, the hub, is our diazonium salt. Aniline was just the rim. It's how we got to the hub. But now we are at the center. From this hub, imagine spokes shooting out in all directions. Each spoke is a different reaction, leading to a different product.
Okay, let's travel down these spokes. This is basically the whole syllabus for this topic, isn't it? So what's spoke number 1?
Spoke 1 is the most famous reaction in this unit. It's the Sandmeyer reaction.
Sandmeyer. We hear this name all the time.
So here, you mix the diazonium salt with a copper eye catalyst. Specifically, cuprous chloride, C2Cl2, or cuprous bromide, C2Br2.
And what happens then?
The nitrogen bubbles off, and the chlorine or bromine takes its place. You get pure chlorobenzene or bromobenzene.
And this is exactly what student B did in our story. She used the Sandmeyer route.
That's correct. Now, there's let's call it a budget version of this reaction. It's called the Gatterman reaction.
Gatterman, is that a different spoke?
You can think of it as spoke 1B. It gives you the same product, but instead of using the fancy cuprous salt, you just use copper powder and HCl or HBr.
So Sandmeyer uses the salt, Gatterman uses the powder.
Yes. Usually Sandmeyer gives a better yield, so it's the preferred one in exams, but you must know both.
Got it. Okay, let's go to spoke 2. What if I want to make iodobenzene? Do I need copper iodide for that?
That's the trick question. No. Iodine is large and, polarizable. The reaction is so favorable that you don't even need a copper catalyst.
Really? So what do I do then?
That is spoke 2. You simply add potassium iodide, Ki, to the diazonium salt and just shake it warmly.
Just shake it.
Just warm and shake. The nitrogen leaves, the iodine hops on. It is the easiest synthesis in the book.
I wish all reactions were that simple. Okay, spoke 3. We have chlorine, bromine, iodine. What about fluorine?
Fluorine is the difficult one. It is small, very aggressive, highly reactive. You cannot use Sandmeyer for fluorine.
So we need a special spoke just for it.
We do. And this is the Balch-Schiemann reaction.
Balch-Schiemann. That sounds quite serious.
It's a 2-step process within this spoke. First, you treat the diazonium salt with something called fluoroboric acid, HBF4. This creates a precipitate benzene diazonium fluoroborate. It's actually stable, which is nice.
Okay, and then?
Then you just heat it strongly. The nitrogen leaves boron trifluoride leaves, and you're left with pure fluorobenzene.
So using this hub, we can basically make any halorine, Cl, Bri, or F.
Exactly.
Yeah.
And remember, trying to put fluorine or iodine directly onto benzene without this hub is a nightmare. Direct iodination is reversible, and direct fluorination is explosive. This hub makes it safe and easy.
That's why it's the super hub.
Okay, spoke 4. This one surprises people. What if I want to turn aniline into phenol?
Well, we mentioned earlier that if you let the mixture get warm by accident, it turns into phenol, right?
Read the decomposition.
Well, spoke 4 is just doing that on purpose. If you want phenol, you just take the diazonium salt and add dilute sulfuric acid in warm water.
Just warm water.
Just acidulated warm water. The nitrogen leaves, the OH group from water attaches, and you get phenol. That's incredibly versatile. You're switching from a nitrogen family to an oxygen family just by adding water.
Correct. Now, spoke 5 is my favorite. I call it the eraser.
The eraser.
Imagine you've done a lot of work on the ring, you've directed groups here and there using the amino group, and now you want to get rid of the amino group entirely. You want to go back to just plain old benzene.
So you want to remove the group and just replace it with a hydrogen atom.
Yes. You use a reducing agent. The most common ones for your exams are hypophosphorus acid, H3PO2, or ethanol.
Ethanol, just like alcohol.
Yes. It can act as a reducing agent here. It donates a hydrogen, the nitrogen gas leaves, and you are left with benzene.
That feels like a magic trick. And for my next trick, I will make the functional group disappear.
It's very useful in multi-step synthesis where you use the amino group to guide incoming groups, and then you just erase it when its job is done.
Okay, we have one final major spoke left. Spoke 6. The colorful one.
Ah, yes. The azo-dye reactions. This is actually a test used in labs to distinguish aromatic amines from aliphatic amines.
This is the coupling reaction, isn't it?
Yes. In this case, we don't let the nitrogen gas escape. Instead, we use the two nitrogen atoms as a sort of bridge to connect the benzene ring to another ring.
Like they're holding hands.
Exactly like they're holding hands. If you react the diazonium salt with phenol in a slightly basic medium, around pH 9-10, the rings couple together to form p-hydroxyazobenzene.
And that has a specific color.
It's a bright orange dye.
Orange dye. Okay.
Okay.
And what if we react it with aniline instead of phenol?
If you react it with aniline in a slightly acidic medium, you get p-aminoazobenzene, and that is a yellow dye.
So phenol gives an orange dye, aniline gives a yellow dye.
The simple way to remember it is PO, phenol orange.
PO, phenol orange. That's good. And these are the dyes we see in real life.
Yes. And this brings us to why this actually matters outside the classroom. We aren't just memorizing colors for the practical exam. 50%. Half of all synthetic dyes, the color of the shirt you are wearing, the bed sheets in your house, are likely azo dyes made using this exact chemistry.
50%. That is huge.
It's a massive industry. But there's something even more important than clothes.
What could possibly be more important than fashion?
Medicine. Saving lives.
Oh, of course.
Have you heard of sulfa drugs? Like sulfanilamide?
I think I've seen it mentioned. It's an antibiotic, right?
It is the grandfather of antibiotics. Before penicillin became widely available, sulfa drugs saved thousands of soldiers in World War II from infection.
And let me guess, you can't make them without our friend, the diazonium salt.
Exactly. The synthesis of sulfanilamide relies on protecting the amino group, doing reactions, and then using this chemistry. You cannot build that molecule efficiently without understanding the reactivity of aniline and its derivatives.
So when student B is doing her experiment correctly in the lab, she's actually using the same principles that built the modern pharmaceutical industry.
Correct. It is not just lines in a textbook, it's the chemistry of health and industry.
That really puts it all into perspective. It's not just about passing class 12, it's about understanding how we build the world around us.
Absolutely.
Okay, we've covered a lot of ground. We've got the mechanism, the temperature, the synthesis wheel, the real world uses. I want to make sure our listeners can do a rapid fire revision right now.
Let's do it. Exam safe clarity lines.
I'll ask the question, you give the clarity line. Ready?
Ready?
Why can't we just add chlorine to aniline directly?
Because the amino group is highly activating. Direct substitution causes polysubstitution. You get a mixture, not a pure product.
What is the main purpose of diazonium salts?
They allow for selective monosubstitution. They let you replace the nitrogen group with one specific group, like a halogen, cyanide, or OH.
What is the most critical condition during preparation?
Temperature must be maintained between 273 to 278 K, 0.5 degrees C, to prevent decomposition.
Name the reaction used to prepare chlorobenzene using cuprous chloride.
The Sandmeyer reaction.
And if we want to make fluorobenzene,
Balch-Schreiman reaction.
finally, how do we distinguish aniline in the lab?
Azo dye test. Coupling with phenol gives an orange dye. Coupling with aniline gives a yellow dye.
Fantastic. If you can answer those rapid-fire questions, you are definitely ready for the board exam questions on this topic.
I would add just one final tip. Students often get confused with conversion questions. If you see a conversion that says, convert aniline to, and the target is a halogen, a cyanide, or a phenol,
What should be their very first thought?
think diazonium first. Do not try to add the group directly. Always go to the hub first, then go to the spoke.
Think diazonium first. That is the mantra for Unit 9.
It really is. It's the detour that saves the entire journey.
Before we wrap up, I just want to leave our listeners with one final image. We talked about student A and student B. Student A tried to, smash through the wall. Student B used a tool.
Exactly. Think of the diazonium salt as a power tool. Imagine trying to build a complex piece of furniture using just a hammer. You'll probably break the wood. That's direct substitution.
It's messy and very crude.
But diazonium chemistry, it's like having a precision laser cutter or a fine drill. It allows you to do very delicate, specific changes to the molecule without destroying the rest of it.
That is a great perspective. Master the hub, and you basically master the unit.
And you will likely score full marks in the conversion section of the paper.
Which is what we all want. Thank you so much for breaking this all down with us today.
My pleasure. Just keep visualizing that wheel.
And to our listener, thanks for diving in with us. Good luck with your revision. Keep your reactions ice cold, and we will catch you in the next deep dive.